Hello, I'm JP and very happy to be with you virtually to present this talk, Postquantum Crypto, Should You Care? So very quickly about myself, I've been doing crypto for quite a while, before it was cool, in academia, industry, I've done some algorithms that you may know, Blake 1, 2, 3. I've done Blake 2 twice in this slide. I wrote some books, and I'm currently working in a company I co-founded, which is called Taurus, and we do technology for companies that want to use cryptocurrency and digital assets in a regulated context and in a secure way. So some quick background that probably obvious to everyone, so I don't need to give details. So quantum computing, now that you know all these equations, you must know that they were not created. The idea of quantum computing was not created for people like me to give talk at conferences. Was not designed to break crypto, but instead in 1981, Richard Feynman, the very famous physicist, he came up with this idea when he thought about whether quantum systems, so the state of subatomic particles defined by the rules of quantum mechanics, whether they can be simulated probabilistically by a classical computer. So he says probabilistically because quantum behavior is not deterministic. So if you have a given state, let's say you don't really know what a particle is. Let's say I have this lemon here, but if I don't look at it, it may be here or there, but it's not determined. The position is not determined. It's not hidden, it's just not determined, which is kind of different. So you have to deal with some probabilities. And when he asked himself the question, he reasoned a bit about whether that would be possible to simulate classically using a normal computer. And the answer, as you can see here, the answer is certainly no, exclamation point. This is called the hidden variable problem. It's impossible to represent the results of quantum mechanics with only a classical universal device. So think about a normal computer, a classical circuit, a Turing machine, any Turing equivalent machine will not work, at least efficiently. So I mean, you can do it, but it would take exponential time, which means it would be practically impossible. So that's when he came up with the idea of quantum computing, which would be something where the computer itself behaves according to the law of physics, and thereby bypassing all the complexity of simulating quantum stuff with non-quantum stuff. So if you have directly a computer that obeys by the rules of quantum mechanics, then you don't really have to simulate it. You just have to encode it and see what happens. So very briefly, I'm not going to explain all the details of a quantum computer, but the main point is that instead of working with bits that are 0 or 1, you deal with quantum bits or qubits that are 0 and 1 at the same time, so to speak. So if you have one qubit, which is, here's a qubit. It's not in a defined state, it's in a state called superposition, which means it's 0 and 1 according to some probabilities that are defined as alpha and beta on this slide, but these probabilities are not exactly probabilities as you know them. They're not just numbers between 0 and 1, there are amplitudes. So that's the name that we give to these quantum probabilities, amplitudes, because they're numbers that can be negative and then can be complex numbers. So complex number of the form a plus bi, where I is the imaginary unit. So if you take the amplitude, the modulus of the amplitude squared, you will end up with a value between 0 and 1, a normal probability, and same for beta in such a way that alpha squared plus beta squared equal 1. But remember that qubits are characterized by these probabilities which are not just positive, but potentially negative, potentially complex, which is completely weird and unnatural, but that's the way it is, that's the way quantum mechanics is. And when you observe this quantum bit, so like I mentioned before, it's in a state that is not determined, it's not hidden, it's just that it's not 0 or 1 unless you observe it, unless you ask it the question, what's your value? And then it stays 0 or 1 essentially forever. So you can generalize this to more than 1 bit, to 2 bits, so you have 4 states, to 3 bits, so you have 8 possible values, and for example to 8 bits, 8 quantum bits, you can call it a quantum byte if you want, and then you have 256 possible values. So you see that the number of possible values grows exponentially. So if you have n quantum bits, you have 2 to the n amplitudes that characterize this state. Now, what's a quantum computer essentially doing? What is computing? So you can simulate it very easily using only linear algebra that you learn in high school, like matrix, vector multiplication, very basic stuff, only linear equations. And essentially, you will transform the state. So the quantum computing is just the evolution of a quantum state, where the state is a list, a vector of amplitudes. And the transformation is essentially multiplying this vector by a matrix, but in such a way that your matrix is characterized by some properties that make it reversible, and in such a way that when you apply the matrix multiplication, the result also ensures that the probabilities will sum to 1 for consistency, because if probabilities don't sum to 1, there are some things quite wrong. And that's pretty much it. But in reality, a quantum computer is, of course, not doing these matrix multiplications. That's just the way you can simulate it. And why you cannot simulate it is because if you have, for example, n qubits, you have, as I mentioned, 2 to the n, an exponential number of amplitudes to keep track of. So you see, as the number of qubit grows, as n grows, you quickly end up with an unmanageable number of amplitudes and of operations. So that's why you can only simulate so many qubits, let's say 20, 30, up to 40 maybe, depending on what you're doing, but certainly not 1 or 200 qubits. Whereas if you work with a quantum computer, you only have to deal with the qubits themselves, but not this exponential number. So that's the idea behind this impossibility result. Now there's this notion of quantum speedup, where something quantum is faster for some definition of speed. So then again, it can be misleading, because we're not talking about speed in terms of pure latency, in terms of CPU frequency. We're talking of speed in terms of fundamental complexity. So for example, you might have a problem that can only be solved with complexity at least big O 2 to the n, some exponential number. And a quantum computer might get you down from exponential complexity to sub-exponential complexity, for example, linear or polynomial complexity, which would mean practical. So in complexity theory, when we have something that is bigger than a polynomial and specifically exponential, it usually means that it's practically impossible to solve this problem in practice. Whereas if we have a complexity that is polynomial, so let's say n square, n cube, or n log n, that is something that is usually manageable in practice. So you might say, okay, but you have n to the power of 200, it might not work, but these cases never happen, well, rarely happen in practice. So you have a website with a list of all problems for which you have a quantum speedup. That's quite interesting. There's also this notion of quantum paradism. So that's sometimes misunderstood. It's not about, if you want to break the key of AES, it's not about computing all the keys simultaneously at the same time, because you heard that a quantum bit can be multiplied by values at the same time. So it's tempting to imagine that you will try all the keys simultaneously and then pick the one that gives the right result. But actually it doesn't work that way. There's something called quantum paradism, but it's quite a different notion. And now maybe one of the biggest, one of the main things you want to remember from this talk is that quantum computer fortunately or unfortunately, will not solve all the computationally hard problems, and specifically, it will not solve the NP-hard problems and not the NP-complete problems. So these are all the problems, all the constraint satisfaction problems, such as SAT, traveling salesman, knapsack problems. Latest problems in crypto are often closely related to NP-complete problems. And if you see it in terms of complexity class, so if I draw the set of NP-complete problems, you see that it's really a part, is disjoint from the set BQP, so bounded error quantum polynomial time, which is the set of problems that a quantum computer could solve efficiently, which is strictly a superset of P, and a superset of BPP and of randomized polynomial type problems, which means that you have some problems that are solvable by a quantum computer, but not solvable by a classical one. So very quickly about quantum supremacy, because I've sometimes been asked this question: what is quantum supremacy about? So it doesn't mean that you will have like a quantum computer in every household, in every street corner. It just means at some point, well, it already happened actually. Well, most likely, quantum supremacy means that we've reached a stage of research where we've managed to run some experiment where some small quantum computer, it doesn't need to be a big one, solve the task, solve the problem strictly faster than any classical computer. And more precisely, it makes something possible, whereas it would be practically impossible by any classical computer. So what Google did is really solve a very concrete problem that is itself defined in terms of quantum computing. And it's just a demonstration that you can do stuff with quantum computers that you would not be able to do otherwise, but it doesn't really have to be useful to be called supremacy, and as far as we can tell today, it's not. So if you want to learn more about quantum computing, I really recommend this book. It's quite not technical, it's relatively accessible, and a really fun read, so yeah, go and buy it. So now maybe the only reason why I've been invited to give this talk at NoNameCon is because you can break some crypto using quantum computers. So let's look at two very sophisticated equations. Here the first is n equal p times q. So if you have p and q, two prime numbers, and you want to compute n, that's about doing one multiplication, which is, well, not a too hard problem. However, if you want to go from n to the factors p and q, that's the factoring problem, which is hard, computationally hard as far as we can tell, using classical computers if you have big enough numbers. So that's, of course, the problem on which RSA is based. Now the second equation, which is slightly more complex but not that hard, is y equal x to the power of d modulo p. So here the game is the following. So you know y, you know x, you know p. So p is a prime number, and you do not know d, and you want to find d. So that's called discrete logarithm problem. It's computing a discrete logarithm. And you can express it in a similar way on elliptic curve groups, where instead of exponentiation, you have multiplication of a point by a number, by a scalar. So these are relatively simple problems. You see them, it's really easy to understand, but it's really hard to solve. And these happen to be fast on a quantum computer, more precisely with qubit complexity, and practically impossible as far as we know classically. And of course, consequence, well, a related result or observation is that these two problems, they are not NPhard, because if they were NPhard, they would not be solvable by a quantum computer. So how bad it is in practice? So if you look at signatures, I mean, that would break signatures, but it's not that a huge deal, because if you see that a quantum computer is about to be used somewhere, then you can just revoke your previous signing keys and issue new signatures, and then you're back on your feet. You minimize the damage, and you don't have to worry too much. You can still wait for signatures in most cases. In terms of key agreements, so mostly Diffie-Hellman. If you look at on paper, it's bad, but in practice, for example, if you look at what the signal application is doing, or what the signal protocol is doing, you combine the Diffie-Hellman protocol with some secret state, let's say to update the keys, to compute new keys. So just breaking the equation that we've seen before, in itself, it would not be sufficient to break everything. It would be part of the problem, but just being able to solve discrete logarithm would not completely destroy the system unless you've really managed to spy on all the conversation from the very beginning of the session initiation to the very end. Now, the biggest problem is encryption, so direct public key encryption or key encapsulation, where you directly take a piece of data, so again my lemon, and you encrypt it. Then the problem is that this encrypted box is out there forever. So an attacker can keep it for like 20, 40 years. And well, ultimately they have a quantum computer, which may or may not happen. They will manage to open it and find your green lemon. So in terms of urgency, it's more important today to switch to public key encryption, Postquantum, instead of signatures, if you care, if that's important for you. Okay. So maybe the good news is that we're very far from this today. The number of qubits that we have in computers, in quantum computers, they're, let's say, between 10 and 100, depending on how you count physical qubits, logical qubits. The number of qubits we have, for example, in RSA key is, let's say, 4,000. For elliptic curves, it's of course smaller. But the quantum base that we would need in a quantum computer is much bigger. It's of the order of millions. Why? So the main reason is that a quantum computer is very sensitive to perturbations from the environment. And like for example, temperature differences. So you have a lot of errors happening inside the quantum system. So you need to correct these errors. So there are some theorems that tell you that in theory you can do it using something similar to error correcting code, which actually we call quantum error correcting code. But you need many more qubits to implement this error correction and to make it scale in such a way that your algorithm will work from the beginning to the end. So you see, we're quite far from something, and it's really an engineering problem to make quantum computers that would scale and that would be able to compute, all these operations that we want them to do. Maybe you've heard about a company D-Wave that claims to be doing quantum computers. Well, they do something that's quite different from quantum computers, and in particular, it will not be able to break RSA, it will not solve discrete logs. So you don't have to worry too much about it as far as crypto is concerned. So yeah, it's not a threat to crypto. Okay. So that's just an excerpt from a paper that tells you, I think it was 2015, 2016, there was some estimate that told you that to factor a number of 1K, 1000 bits, you would need approximately 1.5 million qubits. So there's been other papers, more recent one, that give you a bit more information on this. So now let's move to symmetric crypto. We've been talking about public key. So this applies to RSA, that applies to Diffie-Hellman, to elliptic curves. So all the stuff I said apply to elliptic curves, maybe with the exception of isogenies, which use elliptic curve, but which work on different groups and which seem to be immune to quantum computing. So you know what AES is, I guess, if you don't look it on Wikipedia. So when you want to break AES, most of the time, well, you want to recover the plaintext, but for this, usually you want to recover the key, because if you break the key, you can break all the plaintext. And there's a quantum algorithm called Grover's algorithm that will do something that looks a bit magic, because it will let you search in a list of n items, so for one specific value. So of course the list is not sorted, otherwise it would be too easy. But it would let you search in this list of n values in only square root of n queries, which makes a little sense, because you would expect that if you have n values, you need to look at each of these values individually, because each value can possibly have the value that you're looking for. But then again, quantum magic gives you this quadratic speedup, which is quite nice, and it means that in theory, air quotes, you would go from 2 to the 128 to 2 to the 64 operations, where 128 is the key size of AES 128 if you use 128-bit keys. However, that's really an oversimplification, because in practice you have many more constraints. You have hidden factors in the asymptotic notation. It will not parallelize as easily as normal brute force. And of course, a quantum computer might be slower in terms of latency. It might compute AES much slower than your classical computer would do. So if you look at this paper, for example, it estimated the depth of a circuit in implementing AES. So you need to have AES running in your quantum computer to run Grover. So the depth for the circuit would be around 2 to the 80 gates, which is quite large. 2 to the 80 is quite a huge number. And if each gate is the size of an atom of hydrogen, this is essentially the diameter of the solar system, quite a big computer. So, someone would probably do something smaller, maybe the size of the sun, but that's still pretty large. I think that was in 2015, something like this. So in February 2020, there were slightly better results, but, we're still in the AES here to the 70, so still quite big. But that looks like a 1,000-fold improvement, which is not too bad. Well, anyway, if you want to get rid of the problem, just double the key size, go from 128 to 256, and then you're completely sure that you will be safe against quantum computers. So it's the Grover algorithm that I described is not just the best that we know. We have actual bounds that tell you that we're not going to find better ones in the future. So now, what are the alternatives if you're really worried about quantum computing and you want to, your ciphertext not to be broken in I don't know how many years when quantum computer arrives. So post-quantum encryption, that's how it looks on the internet. So it's not how it looks in reality, of course. It's also called quantum safe or quantum resilient. So you get the idea. It's systems that would not be broken by quantum algorithms. and therefore not broken by quantum computers. So of course it must not completely rely on factoring or discrete logarithm, and it's not just about like taking a piece of paper, writing a new cipher, and say, oh, that looks post-quantum. You need to have some good reasons, let's say good arguments to explain why it would be post-quantum. So, for example, a simple one, or a relatively simple one, is to do something that is NP-hard, and there you're pretty sure that it will not be harmed by quantum computers. Yeah. So why worry about this? So I mean, I don't have a crystal ball. I don't know what's going to happen in the future. I don't even know what's going to happen to me next week. Life is so unpredictable. Nonetheless, you have people who will tell you, "Oh, a quantum computer will be around in 7 years with probability 28%," and this kind of shit. And usually, it's the same people that want to sell you some product to presumably protect you from quantum computers. So I think it makes little sense to make predictions. When you talk to experts behind closed doors, everybody agrees that there are quite big engineering problems, and most people agree that we're not going to have this kind of quantum computing breaking crypto before at least 50 years or 1 century, who cares, if ever. But like when you buy an insurance against a natural disaster, against alien invasion, you just want to eliminate the risk if the probability and if the potential impact is relevant for your business, for what you're up to. Also, you've seen that NSA, so the job of NSA is to protect information systems of the US and also to run some less defensive operations. And in 2015, they published a memo where they say we anticipate a need to shift to quantum-resistant crypto in the near future. So there's no conspiracy theory here. They don't have a quantum computer in their basement. Personally, I don't think they know much more than we do. Again, risk management. When you have to manage a government, a public administration as big as that of the US, and how long it takes to deploy a new technology in a public administration. Just if you want to, change like a new email software, it might take you 10 years. People are still using maybe Windows XP. So that makes total sense from their perspective to consider the threat of quantum computing given their mission. So the NIST agency, which is in charge of creating standards for federal agencies in the US, and which is kind of de facto the global issuer of crypto standards because everybody tends to follow them, and I think they tend to do a pretty good job. So they started a contest to develop new standards that would be post-quantum in the same style as they did in 2000 for AES and in 2012 for SHA-3, which is an open competition whereby they ask researchers all around the world to create and submit new algorithms, and then it's a bit like a destruction derby. Each one tries to attack each other's system and to find out the flaws, and they want to win the competition, and that's a pretty good model for NIST. So I think the deadline wasn't really specified on this slide, but I can give you a small overview of what are the main types of post-quantum crypto that we have, and Latestbase. So if you've heard about post-quantum crypto, you've probably heard about Latestbase crypto. So if you look at a paper about Latestbase crypto, it's quite cryptic. Just what the hell is latest? For most people, it's not really clear, and it's not. But you can express it in very simple terms, and most of the time, it's related to a problem related to learning with errors, which can be expressed in a relatively simple way like this. So let's say you have a vector of secret numbers, which is S in green here. And the goal of the attacker will be the following. So the attacker will get pairs of two vectors, A and B. So A is something that is public, that is known to the attacker, and that is uniformly random. So let's say we have n numbers, A0 to AN-1. And the second vector, so B on this slide, will be the multiplication element by element of S and A. So you see on the second line, you have S0 multiplied by A0, up to S(n-1) multiplied by A-1, but you will not get the exact result of this computation. You will get the result, but with some error. So the error is expressed as an addition of some random values, which in this case are not uniform, but distributed according to a Gaussian distribution, a normal law. So that's what you have on the last bullet here. So each B is equal to SI times AI plus EI, where you know the distribution of the E's. And the goal of the attacker is to find S given possibly a large number of A, B vector, where each time A is different and therefore B is different as well, and E is also freshly computed. So this very simple problem might look easy, but it's actually hard. It's essentially about solving a system of equations where the equations are not really correct. There's some noise, but you don't really know what the noise is. And even the problem of distinguishing this from a random value, of distinguishing B from random values, it's hard. It's actually NPhard. And most of the Latestbase crypto algorithms, they essentially rely on this kind of problem, which is proved to be NP complete. So we can maybe skip this part and fast forward to a few weeks ago when NIST announced the third round finalist. So there's been 3 rounds so far. First round with any submission, second round, and now the last round, which I think is the last one in the competition before NIST select the standards. So in red, we have the candidates based on some latest construction. So I spare you the names. You have Crystal, Kyber, and Tiaro, and True, Saber. In blue, you have the ones based on the code, and in green, the ones based on equations, on multivariate equations. So you see there's many more Latestbase crypto than all the others, which are not really exotic, but slightly different, and maybe they tend to be less efficient. And Psych, Picnic, and Sphinx Plus, they are again different things. Psych is based on isogenies, Picnic on zero-knowledge constructions, but some zero-knowledge proofs that do not use public key crypto, which is quite interesting, and Sphinx is based on hash functions. So a few more words on code-based crypto and multivariate crypto. So code-based crypto, it's quite interesting to see that we're talking about Postquantum, this kind of innovative science fiction-like crypto, but it actually dates back from the late 70s. And one of the submissions, the Michaelis submission, is almost identical to the initial design from Michaelis in 79. So these are only for encryption, and one of the limitations is that the keys tend to be quite large, like a few kilobytes. So the second family, what we call multivariate cryptography, is about relating the security of the system to multivariate equations, to solving multivariate systems of equations, or systems of multivariate equations. So multivariate is, instead of having just A plus B plus C plus D, you have A times B plus A times C times D, and so on and so on. So not just additions, but additions and multiplications. And the main result that we leverage is that the system, the problem of solving quadratic systems, so quadratic is just degree 2, if you have a random system, it's NP-hard. So researchers try to leverage this result to make NP-hard, to make secure systems. It's not, the reduction is not always very, very tight. But to finish this talk, I don't know how much time I have left. I would like to talk about my favorite post-quantum schemes, which are based on hash functions. And I like them because they're much simpler to understand. There's not much math. I'm not a very good mathematician. So I get interested in hash-based crypto. So you know what a hash function is. It's like the most stupid crypto scheme ever. It takes anything. It just computes a random-looking hash value. Of course, the best hash function is Blake's tree. You should use Blake's tree. It's the fastest one, the most secure one. I designed it too, but I'm neutral, don't worry. So hash-based crypto is only about signatures. We do not, and most probably we cannot, create encryption schemes based on hash functions because various reasons. And I mean, they're quite unique because they rely on only symmetric constructions, only on hash functions. There is no mathematical structure behind. There is nothing really complicated. Well, there's something complicated, but it's not really mathematical. And we have very convincing proofs that breaking the system is impossible as long as the hash functions are secure in terms of pre-image or collision resistance. And the good news is that we do have hash functions that we're pretty confident about, such as Blake's tree, for example. But of course, there's a small catch. They tend to be quite slow, at least to issue a signature and to generate the keys. And the signatures, they're pretty big, like a few kilobytes, probably 20 kilobytes. In comparison, an ECDSA signature is 64 bytes. And you also have the problems for some constructions that you need to keep track of a state, and specifically of a counter 1, 2, 3, 4, in order to use a different part of the key every time. But we also have stateless constructions. So in this slide, I would like to describe what is maybe the simplest and the most stupid signature scheme ever designed in '79, and which is really behind all the hash-based signatures that we know and use today. It's really stupid. It makes little sense. It's so simple that it's hard to understand why it's a signature. So first, you generate a key pair. A key pair is first two values, K0 and K1, which would be your private keys, two random values. And the public key is just the hash of these two values, the hash of K1 and the hash of K0. And now if you want to sign a message, so signing just means demonstrating that you, the sender of the message, are the person that actually sent it. So you, as the owner of the private key, you want to demonstrate that you sent this message 0 or 1 by doing something in such a way that the recipient, using the public key, can verify your statement. So what you're going to do, you're not going to make any competition. You're not going to hash anything. You're just, if you publish the message K0, you send K0. If you publish 0, you send K0 as a signature. And if you want to sign the bit 1, you publish K1 as a signature. And then the recipient, the verifier, will just hash K0 or K1 and verify that it matches the public key, the hash of K0 or the hash of K1. Yeah, maybe give you 5 seconds to realize what it does and why it's a signature, so maybe 5 seconds will not be enough. It took me quite some time as well. But anyway, you could realize that it's quite stupid and quite useless because you need as many keys as there are bits in your message, and a key can be used only once. So now you're going to tell me, okay, well, what's wrong with you? Well, there's a trick to sign more bits than 0 and 1. You can hash multiple times. That's why what I explained on this slide. But then again, you have the problem that a key can be used only once. Now you have the problem in, oftentimes in computer science and crypto specifically, you have some problem, and often the solution is to use a tree. And here again, the solution will be to use a tree, to use a hash tree, what people call a Merkle tree these days. And this will be a way to simulate having multiple public keys by only keeping track of one public key. So the way it works, you generate K1, K2, K3, K4, and you hash K1 in K2 and K3 and K4. That's the second line from the bottom. And then you hash the two hashes of K1 and K2 together. And you do the same on the right hand. And then again, you hash the two pairs together, and you end up with the root of the tree. So that will be your public key, the root of this tree. Now, let's say you want to use K1. So the verifier doesn't know K1, but they know the root of the tree. So what you're going to do, you're going to reveal K1, if that's the key you're going to use. And you're going to reveal all the stuff in purple on this slide, which is called the authentication path, or sometimes the proof membership, depending on the context, or the Merkle proof, which will just be a way to demonstrate that this key K1 is connected, so to speak, to the root. So this way the verifier can hash K1, they can hash the hash of K1 and the hash of K2 together, they can take the result and combine it with the last element in purple to go back to the root of the tree. And this way you can demonstrate that you have a key that is connected to this root, and then you can do the same for K2, K3, and K4, and as many keys as you have in your tree. So of course, that's quite simple. But if you look at the hash-based constructions submitted to NIST, Gravity Sphinx and Sphinx Plus, they use not only trees, but trees of trees that they call hyper trees, and construction way more complex than this when you have trees everywhere. But it works. It's quite complex, but it works. I would not say I encourage you to look at it, but if you're curious, it's quite interesting. I think there's quite some optimization research to do in this field. But to be honest, I also think that this kind of hash-based construction is also not very useful in practice because of the complexity and the signature size. Well, to conclude this talk, if I convinced you that post-quantum crypto is a really exciting topic and you want to impress your boss and colleagues and girlfriends and boyfriends by saying you do post-quantum crypto because it sounds so sciencey and cool. So you can actually use some projects. You don't have to code it yourself from scratch. You have some project that provide you with some code that is relatively, I wouldn't say relatively mature, but not too bad compared to typical academic code. So you have the OpenQuantum Safe project, which is the libOQS reference on this slide, which is essentially a fork of OpenSSL integrating some post-quantum algorithms. For Cortex M4 chips, you have PQM4, which is a project with implementations of post-quantum crypto optimized for Cortex M4 chips. And PQClean is like another project that is very interesting, but that assembles different implementations with a kind of unified framework and with some unit testing and test vectors to make it easier to use. And you have some companies like PQShield that also get you dedicated hardware for post-quantum crypto. So let me conclude. So I don't know when it will happen, a scalable quantum computer is built. So I mean, scalable, it's not just the thing we have today with 20 or 50 qubits. So scalable means that it can scale to your problem size. What would happen, and that's very good plot for a science fiction movie or book, then all the public keys would be broken, the world will fall apart, it would be even worse than the COVID pandemic. People will die. I don't know, I don't want to imagine. However, symmetric key crypto will be safe, and the security will be at most half, but I don't worry too much about it. Well, anyway, I mean, if it happens, it would be quite dramatic, as you can see. So the solution, well, you can hide in a cave, and you can only use symmetric crypto and exchange keys using suitcases, but it's not really convenient. So the best solution might instead be to use post-quantum crypto, which is crypto not broken by quantum computers, and we have very good confidence that it will hold for the rest of the time of humanity or the universe life. So the competition organized by NIST is actually running. They just announced the round 3 candidates. Have my favorites, but I will not tell it. It's private information. And you can expect the standards, I think, to be announced. I don't know NIST timeline precisely, but maybe in 1 year from now. And the standard document maybe in 2 years or a bit more. And there's all the software available to play with if you're interested. So thank you very much for following this talk online. You can find me on Twitter. You can probably ask me questions after this talk and find my email. And I would be happy to answer any of your questions about this or the crypto. Thank you.
Yeah, hello again. Jean-Philippe, thank you for your talk. And I believe that people learned a lot about, those scary and crazy quantum computers that will ruin all the internet, because we actually have tons of questions here. First one is, which non-cryptographic problem could be solved with quantum computer?
That's quite a good question. So instead of saying what it will solve, I can say about what kind of problems it might help with, it can speed up. So you have a list of problems for which you have an exponential or marginally a super polynomial speed up. You can find this list online. But more concretely, you have people who are interested in optimizing and improving the efficiency of something that you might have heard about, machine learning. So there's this field of quantum machine learning whereby you plug in some Grover or some other quantum algorithm into your machine learning system, and you get some speed up. So that's one of the potential applications I can think of. I do not endorse this, but that's what researchers have been doing.
Okay, thank you. Do you know companies that claim that they already using post-quantum safe, quantum safe ciphers? What do you think about that? Do you think it's just a hype, and or is this like a real good that company starts earlier?
Yeah, well, I think I fully agreed with the answer of Schneier yesterday. I think he said everything is quantum safe today because of no quantum computer. I mean, most of the time, as I say in the talk, post-quantum security is an insurance against a risk. And as a company, as an organization, you have many risks to consider. And most of the time, this risk will be far from the top of your list. So if you have actually mitigated all the other risks and you have some money to spend and some extra time, you might consider it. But from a pure risk-based perspective, it's usually not a priority. What I've seen sometimes is post-quantum crypto being used as a marketing device or as a differentiator between the competition, because they want to match the expectations of their customer, which may or may not be rational. But I have not seen a lot of interest so far. I have seen a lot of curiosity, a lot of interest for information about it, but not a strong demand for deployment.
So we can say that Dr. Aumasson believes that you should not switch to quantum safe ciphers right now.
I don't have not.
Please, like, solve all the security problems first.
Okay, that's a fair approximation.
Thank you. Talking about Bruce Schneier, also yesterday he told that blockchain is not solution for anything, and this thought he continues to repeat it in blog posts, etc. And he mentioned that like with electronic voting, right, with e-voting, using blockchain to solve e-voting is the dumbest idea ever. What do you think about that?
I think it's a brilliant idea to use blockchain for e-voting, and blockchain everywhere, and it's decentralized, so it will solve all your security problems because it's decentralized, and you have anonymous people running the blockchain, and you have some clumsy code that nobody really audited. So that's a, really good recipe for success, I believe.
I believe you need to show, the sarcasm.
You really have to smile more. You really have to smile more.
Yeah, I'm so bad at it.
Because having like this number of your like followers in Twitter, people start doing the things.
No, I mean, seriously, I would not articulate it in such a good way as Bruce did yesterday, but I essentially agree with what he said.
Thank you.
I mean, e-voting is, seriously, e-voting even without blockchain is, even without blockchain, e-voting is really a complex engineering and procedural problem. It's not just about crypto. Crypto is just a tiny part of the system, and the crypto is maybe the easiest part sometimes.
Okay. I believe that many companies that use blockchain or try to use don't realize that crypto is like it's not the problem here.
Yeah.
Thank you. Another question on topic of quantum computers. How do you think where we can buy the quantum computer?
I think we should have talked of quantum blockchain, or maybe that's one of the next questions. Are there post-quantum blockchains? And
post-quantum blockchains.
Then this could lead to IOTA and to fun discussions. What was your question again? Where can we buy a quantum computer? I mean, there's actually an answer to this, which is in superposition of both being true and incorrect. You can buy something that the vendor will call a quantum computer, but technically it is not. And I think I mentioned it in the talk. It all depends on what you consider a quantum computer. You can also use one from IBM using their web interface. No, I don't think
you can actually use it, right? They have this web interface, and you can actually use it.
Yeah, it's either simulated or using the real quantum hardware. I don't know exactly how it works under the hood, and I don't know if there's a paid model.
But we kind of believe that this is like quantum computer.
Yeah, but anyway, you cannot buy the actual device and put it in your garage.
Yet.
Yeah, you need a very good freezer to cool it down to,
and a lot of power, to run this freezer. Yeah. Okay, let's move. Let's continue with post-quantum topic. You have this book, Serious Cryptography, right? Which is nice and awesome. Do you plan to write a separate book on post-quantum crypto?
Oh, how did you guess? I would say, in all modesty, that I'm not, let's say, competent enough in the details of post-quantum crypto to write a book about it. I have a chapter about it in Serious Crypto, but a large part of what is interesting in post-quantum cryptography is all the latest-based cryptography. and that's really not my field of expertise. However, on your question, I have a second book coming, but which is not about post-quantum crypto, which involves post-quantum crypto. I will talk about isogenies, about lattices, about code-based crypto, but it's not only about this.
So you're saying that for our NoNameCon attendees, you can share some promo code or something for this new book?
Yeah, well, I can say that there will be stuff about quantum computing, description of all the post-quantum techniques, even isogenies. I will explain what is an isogeny, what is psych.
Wow.
Yeah. So I will also talk. I think
when should we expect the book?
I think ETA end of year.
End of year.
Yeah.
So like Christmas present.
Yeah.
Wonderful.
We'll
Okay, so everyone, you have heard that on NoNameCon, Jean-Philippe Aumasson has announced his next book that will be here on end of year, and which covers a lot of cryptographic topics, including how you called isogenic, right?
Isogeny-based cryptography, for example, that's maybe one type of post-quantum crypto that is not mentioned in the presentation, which may be less popular than the others, but which is also quite interesting from a mathematical perspective.
Wow, waiting forward. It should be really fun. Thank you. By the way, talking about books, we have another question here. Does it really pay out to write a crypto book?
That's a good question. So it depends. So the first book that I wrote about the hash function Blake, I think it sold fewer than 100 copies the first year. So needless to say, I didn't.
Fewer than 100, right?
Yeah, less than 100 copies. So yeah, didn't make much money of it. And Serious Crypto, it sold a few, maybe more than 1,000 the first month in comparison. So it's slightly different range. It depends who you write for, if it's for specialists, if it's for a wider audience. But most of the time, I mean, if you're honest about yourself, you're not doing this for the money, you do this because you want to produce quality content. And my motivation was to write the kind of book I wish I had when I started. And I was also a bit frustrated to see that many people did not have the kind of material they needed to do their job or to learn what they wanted to learn. They had either some very poor explanations or some very detailed textbooks for researchers. So I try to address slightly different market segment, so to speak.
Yeah, like honestly, Serious Crypto, it's one of the books we have in our office, and our people that we hire on engineering roles, we gave them to this book and say before, like, don't come back, don't push into master before you read this book.
Okay, so did I do a good job at not answering the question?
You did, yeah. Let's move forward with quantum. What do you think is the best appearance of quantum in fiction, like on screen or in literature?
That's a tough one. There hasn't been many, I mean, as far as I can tell, no, the word quantum is often used to convey the impression of some, scientific stuff or some mysterious, physics-like phenomenon. I used to have a washing machine in my basement, which was quantum. There was the quantum keyword, and presumably what they wanted to say is that it was maybe faster than the non-quantum one. I never noticed a quantum computer. I looked into my washing machine. I didn't find any qubit or any quantum circuit. So yeah, I don't have any good example to say from Moses.
Well, maybe we will have more this kind of movies after
I have to think about
people,
it.
Start like real job on quantum computers. Sure. Let's see. Yeah. Another question. Are you in good shape answering these questions, because we still have a few?
Oh yeah, carry on. I can continue for the next 2 or 3 hours if you like.
Well, that would be a cryptographic overload, but yeah. but let's do our best. So, what would you advise to the organizations that now invest in HSMs? does it make sense to invest in HSMs and talking about quantum cryptography, right?
Well, I think you mean if they use HSM as opposed to investing in the sense of expecting returns from it. I mean, if I want to drink coffee, I get a cup of coffee. If I want to drink wine, I get a glass of wine. So you get the tool that you need for your problem. If the HSM is the best suited solution to your problem, then so be it. Now the question is whether you need an HSM or not. What's your problem? And then again, you have sometimes misunderstandings of HSM. So I don't want to talk too much about it. I've been working in HSM. I happen to know quite a lot about it. But sometimes people believe that the word hardware refers to the hardware implementation. Actually, most of the HSMs, most of the commercial ones, at least, they use cryptography. They run cryptography in software on a microprocessor, and they include no silicon, no dedicated silicon, no FPGA for the cryptographic component. It just happens to be like a box, a dedicated hardware that you put in your rack, or maybe it can be a USB form factor. But most of the time, the cryptography runs in software. The hardware refers to protection against physical attacks. Then
so
again,
people, if you need HSM, like buy HSM and use HSM, right?
Yeah, but just sometimes if you have like a shitty protocol and an insecure key, and then HSM won't save you. Of course, it's part of the solution. But sometimes I've seen it being used not as security theater, but people say, okay, HSM check, we don't need to do our work because we have an HSM, so I can sleep well at night. And the problem is that sometimes they're black boxes, you don't really know what happens inside. So it can be a bit scary depending on the supplier or the company you work with. But
Thank you. Let's move back to Postquantum. Some people are skeptical about NIST procedures and NIST competition about these new Postquantum crypto protocols. What is your what's going on from your opinion? What do you think? What will be the winner? Do you think that these procedures, these competitions, still make sense as a form of selecting new cipher?
So there's a mailing list run by NIST where all these discussions between participants and NIST happen. And I guess so many emails, I started reading them. And I think, for example, Dan Burstein had quite some opinion about this. At some point, there were so many discussions that I stopped reading it. So I haven't followed the latest developments. But what I know, NIST they have limited resources, limited budget to do this. And the problem they have to solve is they have to select one or more post-quantum algorithms to standardize. And their customer, so to speak, is the US federal government. And this will be implemented in the federal government agencies and also de facto in many other companies, many other products. So they have huge responsibilities and it's hard to predict the future. Also in terms of requirements. There's the technology we have today, the chips we have today, the GPUs we have today, but 10 years from now, it's difficult to predict what will be the best or the fastest algorithms in 10 years. You can see it with AES, the AES contest. So I think from my perspective, NIST has been doing a good job. You never do a perfect one. And it's good if people are critical about it. What is good is to be transparent about the selection criteria. So why do you select this algorithm? Why do you not select this one? There was some story about NSA having made some comments, and then people freaked out. Oh, they heard the word NSA, so they start thinking conspiracies and stuff. I think NSA, maybe we don't know what happens behind closed doors, but I don't believe in conspiracy theories. I think NSA is doing their job. I don't think they're up to anything suspicious here.
Yeah, as far as I know, NIST promised to release the initial standard for quantum-resistant cryptography in 2022.
Yes, something like this. And then they have to work on the actual standard document and what precisely what kind of parameters they want to standardize. It's their job.
Okay, thank you. We have two really small questions, and these will be the last ones. Okay, so what's your favorite cipher?
My favorite submission to the Postquantum competition?
No, what's your favorite cipher in general?
Of all time?
Of all time. Only one, like nominate
okay.
only one cipher.
Okay.
Like
So
the award favorite cipher of Jean-Philippe Aumasson will go to.
Then you're asking me a lot. That's when I need to say something very stupid that people don't take it seriously. My favorite cipher, and it's not Caesar cipher. I don't know, but I have some, I don't know. No, there's this cipher that I was looking at the other day. I wouldn't, not necessarily my favorite, but a cryptographic curiosity is the hasty pudding cipher submitted to the AES competition. And it's a very weird cipher with variable block size and variable key size and tweaks before tweakable block cipher. And it includes a number of innovations that seemed a bit crazy at the time, but that now we are more familiar with. So if you want to look at something quite weird and unusual, look, hasty pudding cipher. It was optimized for 64-bit platforms when everybody cared about 32-bit platforms. And now we only care about 64-bit. So I mean, I like this cipher. It has a special place in my inventory of ciphers.
What's the name of it?
Hasty pudding cipher, HPC.
Never heard.
You see, even you don't know it.
Yes, I thought you answered something like base 64.
Okay.
Okay, so
maybe you encrypted base 64, but you should start doing it, or I told you.
Yeah, sorry. Yeah, so the last one. Thank you. The last one.
Last one.
I would like to become a cryptographer. How should I start?
I don't know.
Sorry, that's a tough one. I know.
Well, what I would say is, seriously, it depends what kind of cryptographer you want to do, but I think you need to learn, like in everything. If you start learning a sport or music, you need to learn the foundations and then the other stuff. So maybe learn about like the foundations of cryptography. But if I recommend the books about foundations, it's quite mathematical, like the book by Odette Goldreich, Foundations of Cryptography. But what I've seen is that there's a big difference between people who have this foundational knowledge between what it means to encrypt, what does complexity harness mean. So I would say try to get interested not purely in the ciphers, in encrypting, decrypting, and in TLS and all this stuff, but also in the fundamentals of the problems you're trying to solve in terms of complexity theory. So try to learn from complexity theory. And another thing about NP problems, but stuff like the PCP theorem, and learn about the foundations. What is a hash function fundamentally, and what is a one-way function? It's harder than what is a hard for predicate, all this stuff, and then maybe go from these abstract foundations to the applications. From my perspective, it works better than the other way, but everybody has their own expertise and their own interest.
So if you want to become a cryptographer, you need to learn really a lot of things before you can jump.
And also be careful,
applied.
do not blindly follow cryptographers' advice.
Yeah, especially those that they say during Q&A on some conferences. Yeah. Okay, thank you a lot. It was fantastic Q&A round, and yeah, we will hear this sound, this applause.
Thank you, everyone. Thank you for having me.
Thank you for Q&A.
It was good to do this.
Thank you for joining.
Yeah.
I hope we will, in like physical, and we will show you the beautiful keep and all the things. Yeah.
Cool.